Poster I am presenting for strings 25 is titled A Stringy Dispersion Relation for the Bootstrap. Let's start by looking at the open superstring amplitude where we work in units where the string length is 1. The tree level amplitude looks like simply a ratio of gamma functions, and it satisfies a very interesting property called duality, which is a statement that you can represent it using completely either the T-channel poles or the S-channel poles. These series representations which have only one pole manifest always have a finite domain of convergence. The duality picture is natural from the worldsheet perspective, because on the worldsheet you only have one diagram which you can continuously deform between the S channel and the T channel, and therefore they should really both be the same. This brings us to two important questions. Is there a series representation for the open superstring amplitude that lets you continuously deform between the S channel and the T channel? And is there a QFT-like representation for these amplitudes that satisfy duality? A QFT-like representation would have an S channel plus a T channel plus contact diagrams like we're used to seeing when we do QFT. The answer to both these questions is yes, and it comes from what I call a stringy dispersion relation. If you have an amplitude that satisfies crossing symmetry and has a bounded high energy growth, then you can represent it using this dispersion relation. The A you see in the integrand is the discontinuity of the amplitude across the S channel. And remarkably, there's a free parameter which we call lambda. You don't see any lambda on the left hand side. That's because this representation converges generally for a range of lambda. Now let's apply this dispersion relation to the open superstring amplitude, and we get this remarkable formula which has the S channel pole plus the T channel pole plus the contact diagram. And this representation converges for a range of for all S and T except at the poles where it is expected to diverge. The lambda parameter also lets you deform between the S channel and the T channel representation, because you can pick lambda equal to minus S and cancel the S channel poles, and lambda equal to minus T and cancel the T channel poles. You can also pick constant lambda, and that would lead you to what are called the local crossing symmetric dispersion relations. We also have a similar representation for the closed superstring amplitude, which has 3-channel symmetry, and this also comes from a dispersion relation. Now, let's talk about doing bootstrap using the stringy dispersion relation. The question we want to answer using the bootstrap is that in the space of string-like scattering amplitudes that satisfy duality, is the tree-level superstring amplitude special in any way? And the answer we find is yes, that if you minimize entanglement using the bootstrap, you will land up exactly with the open superstring amplitude. For more details on this, you can visit Arnab's poster. We also use physics-informed neural networks to do bootstrap. This is because one of the constraints we impose using the bootstrap is what is the lambda independence of the amplitude. And numerics always involve some truncation, so these constraints are never exactly satisfied. So you only have lambda independence up to some small tolerance, which we denote by epsilon. But we are a priori never sure how small this epsilon should be. Therefore, it's more appropriate to impose ratio constraints of the form shown, where the ratio is much smaller than epsilon. But now this problem is no longer a linear optimization problem which you could have solved by something like SDPP. It's a non-linear optimization problem, and that is why we use physics-informed neural networks. We use them to do non-linear constraint optimization. Thank you, and for more details about results from the bootstrap and machine learning, please visit my poster.